Hi EP Stats students, this is 11.2, which is kind of another long section. We're doing inferences for relationships. We're going to be using that chi-squared test again. So comparing distributions of a categorical variable. So market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a supermarket compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wine purchased. Here is a table that summarizes the data. So we have the different types of music, and then the wine types that were sold. So does playing Italian music increase the chance of buying Italian wine? So what we could do, we're going to calculate the conditional distribution, remember, so all of them, of the type of wine sold for each treatment. So given no music, let's calculate the distribution of the types of wine. So 30 out of 84, 11 out of 84, and 43 out of 84. So this is kind of our baseline because there is no music given. So now we're going to calculate the conditional distribution given French music. So let's look already. It looks like French music increased French wine sales. It looks like the French music decreased Italian wine sales. And it looks like French music decreased your other wine sales a little bit. Now, are these differences significant? Well, we also want to look at our last one, given Italian music. So it looks like the Italian music did not affect the French wine sales. The Italian music increased the Italian wine sales, but is it significant? And it decreased your other wine sales. Was that enough for it to be significant? Or was this just based off of random chance variability? So then we can make an appropriate graph for comparing the conditional distribution in part A. So we can either make bar graphs, because remember this is categorical data, or we could make stacked bar graphs. I don't really want to do pie charts. Let's do regular bar graphs. So we'll do one for no music. So there's our French, there's our Italian, and this is our other. Now I'm going to stack it next to the French in the red. So our French music, and then with our Italian music. So looking at my graph, it doesn't look like there was too much variation with the French wines. There was a little bit more variation with the Italian wines, and then the other wines had a little bit of variation as well, but I don't know if that's significant. So are the distributions of wine purchases under the three music treatments similar or different? Well, there's some similarities and differences. So we want to give appropriate evidence. So we would look at those conditional distribution numbers, and we already said some of that stuff, like the 36.51, there's about 15% different. This one's about 12% different, so on and so forth. And remember our independence from chapter 5? Well, from our two-way table, we could look at those independents. We would say the probability of A needs to be equal to the probability of A given B. Well, we could check all of those things, but what we're really looking for is our 10% condition. We would say 243 is less than 10% of all wine sold, and that's enough for our independence condition. So then what we need to do is we need to find expected counts. So what percent of the total wine purchased was French wine? Well, so 99 out of 243 bottles were French wine. So that's about 41%. So now we're going to skip this independent section. It just got a little separated. For the treatment of French music, how many people would you expect to buy French wine if its proportion matched that of the total sample? Okay, so this is our expected value. In our French music, 75 total bottles sold, then we would have to say that 40% of those 75 would be French. So we would say 0.4074. That's our percent of those 75. So then we would expect about 31 bottles. Right? So if we go back up to here, we would expect 31 of those 75 bottles should be sold, but we notice, remember, that French music seems to have made it a little higher. So this expected value is a little lower than what actually happened. And you see this observed minus expected happening again. That's that chi-squared test. Well, we could get a chi-squared value of 39 minus 31, which is 8, and then squared over 31, and that would give us our statistic. We do that for our entire table. Well, here's an easier way to get the expected values. We do our row total times our column total divided by the table total, and actually, in fact, that's what we did. Remember, we did 99 out of 243, and then we multiplied it by 75. Well, our row total was 99, our column total was 75, and our table total was 243. So this is a nice little formula if you don't understand how this actually happened, but they should be connected pretty well. So what we could do is we can write the expected values into each cell. So we can put our 31 in there, and we could do that for all of them. We can say 99 times 84 divided by 243. 34. And this parenthesis notation is a widely accepted notation, so you can use it. And then this will be the same, 34. We would say 31 times 84 out of 243. So that one's very close. And we could keep going on. We could find the chi-squared value for each cell and add them up, right? If we did the sum of our chi-squareds, remember it's our observed minus expected squared over expected. So we could do 30 minus 34 squared over 34 plus 39 minus 31 squared over 31 plus 30 minus 34 squared over 34 plus 11 minus 11 squared over 11, and that would just be 0, right? Remember, we're looking for error, and that one didn't have any error to add to our chi-squared statistic. And we could keep going. But you know what? I'm tired, and you already have probably figured out that there is an easier way on our calculator. So what we're going to do is we're going to go through our conditions again. Remember, we have our random, right? We need a random sample of these wines, which if you go back to the beginning, then we can assume that. All right, random assignment for a random sample. Our large sample size, remember the expected values need to be all greater than or equal to 5. And you know what they're going to be. Even though I don't have all of them in there, they're all going to be greater than or equal to 5. And then our independent condition that 243 is less than 10% of all wine sold. Okay, probably that one should be a little boring by now. And then our degrees of freedom is the number of rows minus 1, the number of columns minus 1, and then multiplied together. If you can remember way back, we kind of talked about this when we were filling in two-way tables. Because, right, if you had like a 4x4, you only need one thing, and then you could fill in the rest of your table. Well, for this one, we had 3 rows, so 3 minus 1, and 3 columns, so 3 minus 1. So 2 times 2. There are 4 degrees of freedom. If you think back to the two-way table thing, if we had 1, 2, 3, 4 of those things in there, these 4, then we could fill in the rest of the table because we could get this one, this one, this one, this one, and then this one, and the whole table could be filled in. That's why there's 4 degrees of freedom. Okay, then we also have something different. We have 2 different tests here. They're done exactly the same way, however, the hypotheses are a little different. So the test for homogeneity is there is no difference in the distribution of a categorical variable for several populations or treatments. All right? There is no difference in the distribution. And then our alternative is there is a difference in the distribution, blah, 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 blah. Association and independence is a different test. Sometimes it's called independence. It's typically called a test for association. So this is what we'll be calling it in class. But I want you to know that independence is another name for this test. There is no association between the categorical variables, aka the variables are independent, or there is an association between the categorical variables, so they're not independent. Okay? The only difference is the stated procedure, and you should look at how the data are gathered. Okay? So our association is when you're sampling from the same population. When you're doing homogeneity, you're sampling from different populations. So basically, an easier way to think about this is if it's an observational study, it's association. So in this one, our wine, we have random assigned treatments. So what we're doing is we're sampling from different populations from our different French wines and different types of music, and those are where our samples are coming from. And it's an experiment because you have random assignment. So this is a chi-squared test for homogeneity. Okay, we can check our conditions and all that stuff, but basically I'm just going to show you right now how to use your calculator. So what we need to do is create a matrix. You have to find that button on your calculator. Yours will look a little different than mine. And we need to name this something. So let's call this wine. So we're going to define this variable, and that's what this means. By the variable, you'll see this. And now we would define the variable, and now we can use the variable wine whenever we want. Okay, so then when we go to do our chi-squared tests, from menu, statistics, stat tests, chi-squared two-way test. The goodness of fit was from 11.1. The two-way test is today's. And we're just going to use our wine matrix. And then it runs the test. You need to write all of this stuff down. Okay? And now it'll also give you the expected value matrix. It'll give you, if I go to variables, this is the matrix of all those expected values. These should look familiar, the 34, the 31, 34. So you don't have to do that row times column divided by total anymore if you can remember this. Remember, the comp matrix will give you all the different chi-squared values that were added up to get this 18, which is a very high chi-squared value for 4 degrees of freedom. So that's why our p-value was so small. So it looks like there was a difference in the distribution of wine sales. Okay, that's because it was a test for homogeneity. That's how I would have to say it. So we would reject the null and conclude there was a difference in the distribution of wine sales. Okay, and I'm just going to breeze over this next one. But are men and women equally likely to suffer lingering fear from watching scary movies as children? Well, researchers asked a sample of 117 college students. So we sampled from one population. So this is going to be a chi-squared test of association. Right? We sampled 117 and then we just reported what they were. This is an observational study. Okay, so there's your other hint that it was an association test. So your null hypothesis is that there is no association between gender and fright symptoms, and our alternative is there is an association between gender and fright symptoms. Okay, then we could check our conditions, that it was a random sample, our 10% condition, all expected counts need to be greater than or equal to 5, so we would need to find them and put them into our table. We could do all of that with our calculator. So I'm going to define my fright variable. We're just going to call it fright. We need a matrix. This is a 2 by 2. And then I could run my test. And our p-value is just below 0.05, our chi-squared. Again, we need to write all of this stuff down. 1 degree of freedom. We could get our expected counts matrix. So there's our expected counts, and they're all greater than or equal to 5, so we know we're good. And this one, because it is less than 0.05, we would be able to say that there is an association between gender and fright symptoms. Okay, again, I'm glossing over all the details, but I wanted to get you the idea. All right, we'll have plenty of practice of this in class.